Speaker is Aman Nougrahiya, and he'll be presenting his work on homeostasis. Here we go.
Great. Thank you for the introduction. Good afternoon, everyone. All right, so in this talk, I'm going to discuss about homeostasis, which is a new compiler design using which you can create self-stabilizing compilers. What are self-stabilizing compilers? We'll look at it. So this work was done with my advisor, Krishna, who's here at PaceLab IIT Madras. So modern compilers typically perform a large number of analyses on a program under compilation. The results of these analyses, which we refer as program abstractions, can be many. For example, AST, constant propagation information, control flow graph, symbol table, and so on. Initially, everything is fine, and these abstractions are stable. We define an analysis to be stable or program abstraction to be stable when it is consistent with the state of the program. Now here comes an optimization, let's say constant propagation and dead code removal. Typically, these optimizations inspect the state of the program abstractions, and then, depending upon various checks, they perform the transformations. The issue is, as soon as the transformations are performed, for example, here, the pass can easily identify that y is actually 3.0. It performs the replacement, all well and good. But now the abstractions are not stable anymore. They are not consistent with the state of the program. Why is this an issue? I have already done the transformation. The problem is, an optimization can have multiple such phases of inspections and transformations, and a compilation process may have multiple such optimizations. So whenever a transformation is performed, the next inspection phase may read incorrect values of the program abstractions, and that can lead to incorrect or inefficient optimizations. What is the solution? Stabilize the program abstractions. So for any given optimization pass, let us say O, we have three key questions to address. First is, which program abstractions need to be stabilized in the context of O? Second, where do we stabilize each program abstraction in the code of O? And third, how do we stabilize each program abstraction? In this talk, we'll mainly focus on the first two questions. And these similar questions need to be addressed whenever we add a new program abstraction to the compiler framework, which is a very, very common scenario. And addressing these questions manually can be complex and error-prone. Let's look at some real-life examples now. So we have two code snippets from LLVM and OpenJ9. In the first code snippet, we see a standard boilerplate code, which I think those of you who have worked with LLVM would know. So in this code, for example, the pass writer is specifying that, okay, these are the abstractions that must be stabilized, that are required to be stabilized before I run this pass. So this can be, like, for example, dominator tree or alias analysis results and so on. Similarly, they also specify that these are the abstractions that need not be invalidated once the pass is run, because by default LLVM invalidates all the abstractions at the end of the pass. In the second example, we can see from OpenJ9, this is about scape analysis. So we can see that the pass writer is sort of keeping track of whether the program changes have occurred. And then accordingly, after identifying that, okay, used of information, value number information are the abstractions that need to be stabilized. After doing that, now they are checking that, okay, if there are some changes, let's just invalidate the information. Now here is the key point. None of this code in LLVM, OpenJ9, none of this code corresponds to the actual algorithm or the core logic of the passes that the pass writer wants to implement. Our proposed solution, let's remove all this code, attain self-stabilization through homeostasis. Homeostasis is a design principle which is applicable to all object-oriented compilers. We can create self-stabilizing compilers using that. It captures all the program changes automatically in a centralized data structure in a compressed, efficient form. And whenever required, it triggers stabilization for these various program abstractions. And the interesting thing here is that to ensure self-stabilization, neither the optimization pass writers nor the analysis pass writers have to specify even a single line of additional code specific to the task of stabilization. So now let us look at how optimization pass interacts with various program abstractions in the context of homeostasis. So during the transformation phase of an optimization, homeostasis enforces that all the transformations must happen through a fixed set of elementary transformations. These elementary transformations will capture the program changes, and that will be used later by the program abstractions. In the inspection phase later, homeostasis ensures that whenever a getter is invoked, it always returns the stable value of the program abstraction. It does so by internally invoking the stabilizers whenever required. So let's look at the template of an elementary transformation, getter, and stabilizer in the context of homeostasis. An elementary transformation acts as a link between optimization and various program abstractions. It captures the program changes and conveys to the program abstractions. Now let's look at an example of an elementary transformation. This one replaces the body of a while statement. Okay, so there are 4 key steps. In the first step, we just save all the nodes and edges that may have been added or removed from the IR of the program in response to removal of the old body. Then we perform the actual update. Then we again save the nodes and edges that could be impacted because of addition of the new body. And finally, the elementary transformation communicates with the program abstractions about these changes. To do so, so here base PA is the superclass of all the program abstractions. We just iterate over all the analysis and set a bit. Stable status, it's unstable. And then in a centralized data structure, we save all the program nodes and edges that have been impacted by this change. Now the interesting thing here, or an important thing here, is that for a given grammar, there is always a way to come up with a fixed set of elementary transformations in terms of which all other transformations can be expressed. Moving on, so here is a template of a getter. So getters of any program abstraction will always return its stable value. There's a standard template to follow. The rest of the code of a getter remains the same. We just add this simple piece of code here, which says if the stable status is unstable, just stabilize the abstraction first. And this is how the stabilizer looks like. Stabilizer, as the name suggests, will trigger the actual stabilization of the program abstraction. We support both the lazy modes of stabilization, that is the default one where we just invalidate the results and fully recompute the program abstractions, or incrementally update the solution with the given program changes. So the program changes which are required in update mode are provided by homeostasis. Now, as we can see in this template, there are 2 methods, compute and handle update. So in the design of homeostasis, compute refers to just the standard implementation of any algorithm. And handle update, if the pass writer wants to opt UPD mode or the update modes, handle update is the place where we have to provide the implementation of how program changes will impact the given solution. Okay, overall, while working in a homeostasis-enabled compiler, these are the additional tasks that we need to perform. For a compiler base writer, the first task is define the fixed set of elementary transformations. And second is create the superclass base PA. These are moderate efforts, but they are required only once per compiler. Then analysis pass writer simply have to follow the structure defined by base PA. The structure is defined in the paper. These are very minimal efforts and they are required once per analysis. And optimization pass writers, interestingly, they don't have to do anything else. So as we even discussed earlier, the code of LLVM and OpenJ9, the snippets that we saw, none of that is required once we retrofit LLVM and OpenJ9 with homeostasis. Once these tasks are performed, homeostasis ensures that all the reads of a program abstraction will return stable values. What's the proof? Well, it's in the paper. So formal description of homeostasis and its correctness proof are present in the paper. And the paper also discusses about how it efficiently captures the program changes in a centralized compressed list. And it also discusses how handling pass dependencies is automated. You don't have to specify that, okay, this is the order in which analysis should be run. We also discuss how we handle homeostasis in the context of multi-level IRs and how we can use it for procedural compilers such as DCC. So now I'll quickly discuss some results and implementation. So we have implemented homeostasis in the IMOP compiler framework. IMOP is an open source compiler framework for OpenMPC programs spanning over 170,000 lines of code. For evaluating our implementation, for evaluating homeostasis, we also implemented a generic framework for performing iterative data flow analysis. So this algorithm is a simple extension of the work by Pollock and Sofa from 1989. And we have evaluated homeostasis on bare-LM, which is a set of real-world optimization passes for removing OpenMP barriers. We have performed evaluations for 24 benchmark programs across these 4 benchmark suites, and we provide the following evaluation dimensions. First is ease of use of homeostasis as compared to manual stabilization. Second is how does homeostasis perform with its given lazy stabilization in terms of compilation time and memory footprint. And third is empirical correctness of our implementation. Okay, so now let us understand how do we quantify the notion of manual stabilization efforts, right? So if you recall, there are 2 key questions: which program abstractions to stabilize and where to trigger the stabilizations. So for the first one, we simply define the notion of a critical program abstraction. It is a set of those program abstractions that may be rendered unstable because of transformations done by the optimization pass. And by performing instrumentation in the IMOP compiler framework, we found that there are 7 such critical program abstractions. Now the next question is where to trigger the stabilization. So the most naive way to do that, if you'll think about it, is to simply trigger the stabilization whenever any elementary transformation is triggered, right? So there are 84 such points in bare-LM, which translates into approximately 1 change point per 29 lines. This is quite huge, right? But then if you think about it further, an experienced programmer would insert or rather trigger stabilizations only at relevant change points. That is the last change point in a series of transformations after which a given abstraction might be read from. Even then, the maximum number of RPs or relevant change points that we obtain in bare-LM is 70. So with manual stabilization, pass writers will have to first of all identify what are these 7 critical program abstractions out of hundreds of program abstractions in a real world compiler. Second is they will have to identify and handle all these relevant change points, these 70 relevant change points in thousands of lines of code. And this is just for the optimization pass that we use. If the optimization pass is much larger, then identifying these relevant change points can be very complex and error prone. With homeostasis, they don't have to do any of this. They do not need to identify the set of critical program abstractions or the set of relevant change points. Okay, so for performance evaluation, we have studied 4 modes of stabilization, which vary across these 2 dimensions. The first one is how do we stabilize the program abstraction, and second is where do we trigger the stabilizations. So the expert developers would typically trigger the stabilizations at relevant change points. This is obviously an approximation because depending on the domain information, we might be able to reduce it further, reduce the number of triggers further. And homeostasis performs it lazily whenever a getter is invoked for any given program abstraction. And as discussed earlier, we have 2 ways in which we can stabilize the program abstractions: either invalidate and fully recompute the solution, or incrementally update the solution with the help of program changes given by homeostasis. So we take RPINV as the baseline in the graph over here. So this is actually a single graph which contains information for 24 benchmark programs under study. And we have these 3 configurations that we discussed, which we saw in the previous slide. And this shows what is the speed up in the compilation time when we try to stabilize any of the data flow analysis. So we can see that the maximum gain with update mode is 30.64 times with the geo mean of 8.84 times. But that is expected, right? I mean, the update modes will take much lesser time than the full recomputation mode. But then for that, let us look at LZINV, which is still the invalidate mode. Even there, we see a maximum improvement of 2.29x for stream and a geo mean improvement of 1.43x. Why? Because the number of stabilization triggers have reduced. And obviously, this also depends on how many nodes are getting reprocessed in the iterative version, in the incremental version or the exhaustive version of IDFAs. Okay, so to conclude, we studied more than 50 real-world compiler frameworks, and we found that stabilization issue is prevalent across all of them. And in this work, we have presented homeostasis, which attempts to resolve this issue using the notion of self-stabilization. We claim the generality of homeostasis by providing the formal definition and its correctness proofs. Please refer to the paper for more details on that. And we have affirmed its feasibility by implementing it in the IMOP compiler framework. And we have affirmed the efficiency and ease of use of homeostasis by showing the empirical benefits that we receive with homeostasis while applying it on a real-world set of optimization passes. Homeostasis is applicable to all the object-oriented compiler frameworks, and so yeah, with that I'll conclude the talk. And just a personal note, I'm finalizing my thesis, I'm in the job market, so I'm interested in exploring research positions in the field of compilers, PL, and SE in industry and academia. Thank you.
Thank you for the talk. I'm not sure if I missed it. What kind of program abstraction when you keep a reference to?
So any kind of, by the word abstraction, we mean to refer to any analysis results. It can refer to anything like a call graph representation of the program, or a control flow graph, or points to analysis results, or let us say constant propagation results.
I mean,
yes.
When you are saying you are building up the link between the program changes into a program abstractions.
Sorry, can you please repeat?
So I might misunderstanding the method here. Like in one of the slides, you mentioned about the encoding or building up the link between the program changes into program abstractions.
Yes.
So can you talk a little bit more about
yeah,
that?
so I mean, the way we look at a program is we treat it as a graph, and whatever changes are being performed by the optimization pass, they can be represented as simply the set of nodes that are added and removed, or set of edges that are added and removed.
Yes.
Once the elementary transformation captures this information, it can, in a centralized data structure, preserve these information. Now, every program abstraction will have a pointer to this data structure, and whenever we require to stabilize it, it will take the net set of program changes and then either perform the incremental update, or it will do a full recomputation. But I think I'm not answering your question. Can you please repeat it? I'm sorry, I'm unable to understand.
I don't see, maybe we can talk offline if it's too complicated.
Thank you. Thanks for the question.
Thanks.
Okay.
Hi, thanks for the nice talk. Do you have a sense of how many bugs there are in compilers? Because people have to do this manually normally. Does it lead to actual miscompilation? And
how many bugs? Okay.
Yeah, I mean, is it common that people mess up with this?
Yeah, so in the paper we have, like, for example, so we looked at the GitHub repo of LLVM, and over the period of, I think, 5 to 6 months, we were able to find 14 commits which were bug resolving. I'll show one of them here.
And these are bugs you would have prevented, I suppose.
Yes, because there is no code to write, so we cannot add bugs if there is no code. All right, so
cool.
Yeah, so let me go on to the next slide. Yes, so see, this is about a performance bug. So here in fixup state point caller saved.cpp, this file in LLVM, the user realized that they can preserve the CFG. So this is about a performance bug that, I mean, it was getting invalidated, but now they're saying that, no, this preserves the CFG. And here's a correctness bug, where we say that we were not keeping track of program changes correctly. They were saying that, no, there are no program changes, but then later the user realized that, no, it was a program change, and this should have actually invalidated or stabilized the something. Yeah, I mean, I think it doesn't say, but yeah. So whatever is the abstraction that could have gotten impacted, right? It wouldn't get triggered. The stabilization would not get triggered if we are not able to even catch the program changes. So yeah, I mean, this is just an example, but in the paper we have references to more commits.
Okay, very good. Thanks.
Thanks. Thanks.
All right, let's thank our speaker again.